Welcome to video 43 in our series on tensor calculus. In this video, we'll explore the possible symmetries of tensors. This will lead to the definition of a new tensor calculus object known as the permutation symbol. Suppose we have this expression, t, I, j, k, and we're going to be discussing everything as it relates to three dimensions. So this would be a system with three free or live indexes, each of which could assume a value of 1 to 3. So this is really a collection of 27 different elements. Now, it may or may not be a tensor. That's unimportant for the discussion we're going to have here. But it's, just think of it as a collection or a system of 27 elements that are managed by the use of these three indexes. Now, let's say we know that this expression is such that if I flip the first two indexes into the reverse order, I'm going to get the same value. In other words, the expression is symmetric with respect to the first two indexes. That means that something like 1, 2, 3 is going to be equal to the element 2, 1, 3. We've run into this sort of thing before. And again, we say that it is symmetric with respect to the first two indexes. But then let's say we also learn or figure out that this expression is also symmetric with respect to the second and third indexes. That would mean we could flip j and k here and get this expression, t, I, k, j. And since this one would be equal to this one, then they're all three equal. All right, well, where does this lead us? Well, let's look at this expression. Since we know that we could flip I and j and get the same value, that means we could flip these two indexes and get t, k, I, j. And then we could flip these two indexes because we know it's symmetric with respect to those, and I'd get t, k, j, I. And all of these would be equal to each other. And that means that this one is equal to this guy. And that looks like we just flipped the first index with the third. So where I'm going here is that if such an expression is symmetric with respect to the first two indexes and the last two indexes, then it has to be symmetric with respect to the first and third. So we can add that to our list here too. This is equal to t, k, j, I, like that. Okay, now what we've got going here is an index system in which if we flip any two indexes, doesn't matter which two we flip, we're going to get an expression or value that's exactly identical to what we started with. So anytime we have something that has that property where you can flip any two indexes without changing the value, we say it is totally symmetric. Now the thing about a totally symmetric expression like this is that it's impossible for all of the 27 elements within the system to be unique. Because obviously if we had term 1, 2, 3, it has to be the same as an expression 2, 1, 3. And for that reason, those two have to be the same and they can't be independent values. Well, if you play around with this a little bit, you'll discover that with a totally symmetric system like this with three indexes, you're going to have a maximum of 10 unique elements. With those 10 values, you're going to find that the others, the symmetric elements that pair up with it will be predetermined by these restrictions. We say that such a system would have 10 degrees of freedom. Okay, let's look now at another expression. Looks similar. This would be S, I, J, K. And this time, instead of being symmetric with respect to two indexes, we're going to say that it's anti-symmetric. So Sijk is going to be equal to the negative value of Sjuk. And we say then that the expression is anti-symmetric with respect to the first two indexes. Well, as before, let's say that we also discover that it is anti-symmetric with respect to j and k. That means if I start with this, flip j and k, I'll get a negative value, s, I, k, j. Flipping the indexes j and k will switch the sign of the expression here, as it did when we switched I and j there. Well, let's see where that takes us. Well, let's go with this last term here and switch I and k. And what did we learn about switching I and k? Well, it changes the sign of the expression. So switching I and k will give us a positive k, I, j. And then we're going to flip these two. And again, we said that flipping those two will cause the sign to change. So now we're back to a negative s, k, j, I. And all of these are equal to each other, as before. But now this is equal to this. And it looks like when we flip I with k here, we're going to get this, which means we have to add that to our equation as well. Meaning if the expression is anti-symmetric with respect to I and j and k, it must also be anti-symmetric with respect to I and k. So we'd have k, j, I. All right, now any system such as this, in which we can flip any two indexes, causing the sign to change, is said to be totally anti-symmetric, or skew-symmetric. Now we said a system that is totally symmetric is going to be restricted in terms of the degrees of freedom because of the various symmetric relationships. We said that this expression with three indexes that's totally symmetric is going to have 10 degrees of freedom. Well, let's investigate what the restrictions are on a totally anti-symmetric system, or a skewed symmetric system. Well, the first thing we look at is this. Suppose we have, well, as example, S112. And if we model it with this term, and we're going to have I is 1, j is 1, k is 2. Now let's plug those in over here. We'll have negative s, j is 1, I is 1, k is 2, and those two are going to be equal. Well, the only way this could be true is if they're both equal to 0. Well, let's try something now where j and k are equal, like S1, 2, 2. And if we model it after this, and then we go over to, say, this expression over here, we're going to have negative s, 1, and j and k are both 2. So we'd have this. Again, the only way this could be true is if they're both equal to 0. And you'll find this to be true that anytime we have a duplicate index in any position, the value of the expression has got to be 0 because of the anti-symmetric relationship. Okay, so the only non-zero values in our system here are going to be those in which we have no duplicate indexes. And since the values of each index can only be 1, 2, and 3, that means that the non-zero elements in this system are going to be some permutation of the numbers 1, 2, and 3. It could be any one of 6 expressions because there are 6 permutations here. But out of the 27 elements we're talking about, only 6 of them, the 6 permutations of this, are going to be non-zero. That means that 21 of the elements within this system are going to be 0. Only 6 are going to be non-zero. All right. Well, let's dig a little deeper here. Let's look at this first. Let's say that S1, 2, 3 is equal to some scalar value, let's say, oh, I don't know, just S. Then if we flip the first two indexes, S2, 1, 3, well, according to our rules up here, we flip any pair of indexes, it's got to produce a negative value, so this would be negative S. Now let's go back to the original and flip the second two. That gives us S1, 3, 2. Well, that's also got to be negative S. And now let's flip 1 and 3. We'd have S3, 2, 1, and that equals negative S. So here are the three ways that we can flip the indexes once, and they all produce a negative S. Okay, but now let's take the second term, this guy right here, and flip the second two indexes. We get S, 2, 3, 1, and because we're flipping a pair of indexes, we have to change the sign, and that becomes positive. All right, let's do the same thing now with this expression. We're going to take S321 and flip the indexes, and we're going to get S312, and because I have a negative here, this one's going to be positive like that. Okay, now what I've got at this point is all of the permutations for 1, 2, 3. You got 1, 2, 3, 4, 5, 6. Those are the 6 ways that we can permute indexes 1, 2, and 3. Okay, now the interesting thing is here that in every case, in all 6 cases, we get either S or negative S. So, since we know that all the others have duplicate indexes and are 0, we'd say that an anti-symmetric system like this, or a skew-symmetric system with 3 indexes, is always going to have only 1 degree of freedom. Once we establish the value of S1, 2, 3, all the other elements are determined. The other 5 permutations here are determined, and then the 21 elements that have duplicates are also determined to be 0. So we have only 1 degree of freedom. Now, let me point out that each of these 3 guys right here were obtained directly from here with just 1 flip of the indexes. So we had 1 flip to get to these. But to get these down here, we first had to flip the indexes this way, and then we flipped the other 2 to get here. So it took 2 flipping operations to get back to positive again. The same sort of thing happened with the last. We started here, we flipped it to here, and that one to here. It took us 2 flipping operations to get back to positive again like that. And of course up here we didn't have to flip anything, so that's a 0. And here's my point, is that these guys would be known as odd permutations. And these would be even permutations. So any even permutation, this one, or this one, will yield a positive value of S, where the odd permutations, these 3, would yield a negative S. Now you can play around with it on your own and see that if I were to flip this one again, either of the first 2 or any way you flip this again, you're going to find one of these 3 guys up here. One that it's going to duplicate what you've already done. We can't produce any new permutations of the combination of 1, 2, and 3. So any flipping you do here will go back to one that you've already done. So it's impossible to arrive at a negative S value without doing an odd number of flipping operations. Likewise, it's impossible to come up with a positive value of s without doing an even number of flipping operations. And that's why we can classify these as odd and even permutations. Now with that background, I want to introduce the definitions of two new objects that we call permutation symbols. Now both of these objects are defined exactly the same way. Number one, they are both skew-symmetric. So skew-symmetric. And the value of our primary position, E1, 2, 3, is equal to E1, 2, 3 is equal to 1. Okay, now what does that mean? Well, it means, first of all, that the value of either of these is going to be 0 for duplicate indexes. And the value will be 1 for even permutations, and it will be -1 for odd permutations. So the value of either one of these expressions, these permutation symbols, is going to take on one of those three values. So from our discussion before, with three indexes like this in 3 dimensions, there are going to be 21 combinations here, permutations in which the value is going to be 0. There are going to be 3 of them in which the value is 1, and 3 in which the value is odd. All right, now what this does for us is it allows us to write an expression like this, Sij, where this is our skew-symmetric system, could be written now as Eijk times our scalar value s. And we don't have to expand out all the individual terms. What it does is it allows us to determine the sign of the permutation of the indexes so that this equation makes sense. All right, now the reason that we have two different permutation symbols is that we do the same thing if we're going to handle an expression like this, where the indexes are in the upper position. We simply use the other permutation symbol, Eijk, so that our indexes match up across the equal sign like that. Now we'll soon discover that these permutation symbols give us a convenient way to represent the value of determinants. But we'll save that analysis for the next video. For now, we'll just conclude this video with a brief review. We started with a discussion of tensor symmetry. We said that if we can flip the order of a pair of indexes and the value does not change, that the tensor is said to be symmetric with respect to that pair of indexes. And if that's true for any pair of indexes, if we can flip I and j to get this, j and k to get this one, or I and k to get this one, if none of those operations changes the value, then the tensor is said to be totally symmetric. We also said that in such a case, the number of unique values for tensor components is limited. We said that for a tensor with 3 indexes like this, there are 27 components to this tensor, but there can only be 10 unique values. We said that such a tensor has 10 degrees of freedom. Then we talked about the situation where flipping the indexes actually causes the sign to change. When that happens, we say that the tensor is anti-symmetric with respect to that pair of indexes. And if that's true for each pair of indexes, flipping I and j, or j and k, or I and k causes the sign to change, then the tensor is said to be totally anti-symmetric or skew-symmetric. We pointed out that if such is the case, then there's only 1 degree of freedom. That the only way that any of these can be non-zero is if the indexes have unique values, such as 1, 2, 3. If there are any duplicates in the indexes, the value is going to be 0. And then if there are no duplicates, then half of the values are going to be positive and half are going to be negative, depending on whether the order of the indexes are an even or an odd permutation of the unique values of the indexes. And with that, we went on to define two new symbols, the permutation symbols. We said that Eijk in either of these forms is going to be a system that is skew-symmetric, and the primary position is going to be equal to 1. That means that the value of each of these symbols is either going to be 0, 1, or negative 1. The value is going to be 0 if any of the index values are duplicates, and it's going to be 1 if the index values are unique but represent an even permutation, and negative 1 if the indexes are unique in an odd permutation. Alright, in the next video we're going to build on this and develop syntax for determinants.